Okay, the focus of my talk will be about the use of a new platform of materials, polymeric materials. They are called polyurethanes because they contain the urethane bond in their chain. But together with this bond, they can contain blocks made of other materials, such as polyesters or other materials that can be used or are already used in medicine. The advantage of combining these blocks in the polymeric chain is that we can introduce several different functions in the polymer, and this is ideal when you want to use this polymer to create 3D environments to interact actively and proactively with cells. And these materials can be therefore implemented to application in biomedicines such as tissue engineering, drug delivery, cancer therapy, or the creation of organ models, which is the area in which our work has been developing more recently and will be the more important topic of my talk today. Okay, models, in vitro models, are systems that people are developing to replace animal experiments. The reason for this effort are mainly two. One of them is the fact that using animals for testing is to some extent unethical, so there are a lot of effort to reduce these trials for ethical reasons. But the other reason, most important reason, is that these animal models are not predictive enough with respect to what the human body will do with respect to a drug or a therapy. Therefore, these models are realized by using human cells usually, so that they reproduce the human tissue, the human organs in a more close way, in a more reliable way. Our work as material scientists in this effort is the realization of 3D environment by using polymeric materials mimicking the cellular environment that you will find in the body. So for this reason, polyurethanes are very useful because you can, in the blocks I was describing before, you can introduce specific function where you can bind also biomolecules or other factors that can interact with cells and induce cell differentiation in the case of stem cells, cell adhesion, cell proliferation. Everything is directed to the creation of a environment that reproduces to some extent the natural environment. This would be an ideal in vitro tool to test the effect of drugs or the development of pathologies. In the talk, I will also describe how we can develop human models of tissues for young people, so healthy models, but also to modify these models, also by playing with the structure, the chemistry, and the design of the material and of the scaffold structure, in order to have models of the aged diseases, aged tissues. And this will allow to have also a tool to investigate cures which are specific for the elderly people, which are specific for a tissue which is not younger anymore. And this is a key issue also in medical research, has been highlighted also by the H2020 calls, the recent calls for European projects. Okay, so this is the original goal we had in the development of polyurethanes. We saw that the materials that were present so far in the application of scaffolds for tissue engineering and regenerative medicine, these materials were not sufficiently functional and were not matching all the requirements of this challenging approach. Therefore, we selected these polyurethanes that contain some of the features that the approved material had, such as polylactic acid, for example, but we included, by using this chemistry that combined different blocks, also other features, so we can more precisely tailor mechanical properties surface properties and provide chemical and biochemical cues to the cells, so that we develop biomimicry with 3 tools, which is more effective than only mimicking the surface chemistry. Of course, polyurethanes are also versatile materials that can be used in rapid prototyping techniques because they're thermoplastic polymers, thermoplastic materials, so they can be processed from the melt, and we can use, therefore, melt processing techniques to design scaffolds with precise geometry with this kind of techniques. Nevertheless, we also use other approaches to create sponges by phase inversion techniques, so that we have a porous material in which cells can grow, proliferate, and differentiate eventually.